Okay, so we're going to continue looking at uses for derivatives. We're going to look at curve sketching, which we've kind of seen an intro to already with 4.1 when we were looking at finding maximum and minimum values. But we can find even more information using the derivative. So this was one of the first uses of calculus when it was developed, was to accurately sketch more complex curves. And even though we can do that on our calculators now, we're still going to look at that underlying idea because that concept can then be applied to other applications. Okay, so if we take the first derivative of a function, if that first derivative is positive, the curve is going up. If the first derivative is negative, the curve is going down. And if the first derivative is 0, you have a possible maximum or minimum value. That's where we have our critical points. We can also look at the second derivative and get some information. If the second derivative is positive, the curve is concave up. If the second derivative is negative, the curve is concave down. And if the second derivative is 0, we have a possible inflection point. An inflection point is where the concavity changes. Okay, so you can take a moment to look at Theorem 4 in your textbook on page 205 and 206 to see the first derivative test. So the first derivative test allows us to find local extreme values. We take the first derivative, we can factor, and this allows us to find our critical points, 0, negative 1/2, and 4. And we've already seen this method before, we just hadn't given it this name, first derivative test. So we make our number line, and using our number line, we check values of the first derivative. So we check a number to the left of negative 1/2, so we can check negative 1. That's positive, so our function is going up from negative infinity to negative 1/2. Check a number between negative 1/2 and 0, like negative 1/4. We get negative, so then the function goes down. A number between 0 and 4, we can check 1. We get negative, so the function is still going down. And then if we check a number to the right of 4, we get positive, now the function is going up. So we can conclude then that there's a local maximum when x is negative 1/2 because the function is going up and then down, minimum when x is 4 because it's going down and then up, and there's no extreme value when x equals 0 because although it was a critical point, the function continued going down. And here's what that graph actually looks like. And you can see those extreme values. So you can see if we kind of zoom in there when x equals 0, that's where we had a critical point. The slope levels off for one moment, but then it continues down, so there's no extreme value. Okay, now we have the second derivative test. So take a look at Theorem 5 on page 211 in your textbook. The second derivative test just gives us another method for finding extreme values. So we have to take the first derivative, factor, and find our critical points, just like we did on that last example. So there's our critical points. And then using the second derivative test, just like the name would imply, we can take the second derivative of the function. This is going to tell us concavity. And we check the concavity at each of our critical points. So concave down when x is negative 1/2. F double prime of 0 is 0. F double prime of 4 is positive. And so by the second derivative test, there's a local maximum when x is negative 1/2. And the way we think about this is there's a critical point, and so the slope is 0, and the curve is concave down. If it's concave down and there's a slope of 0, there must be a maximum value when that slope is 0. There's a local minimum when x equals 4, because again, there's a critical point, so the slope is 0, and the second derivative is positive, so it's concave up, which means there must be a minimum value there at that critical point. But then when x equals 0, although there was a critical point, f double prime is 0, so it's an inflection point. There is no maximum or minimum value at that point. Okay, so we want to go ahead and try to graph this equation. We can factor it to find the roots. We can take the derivative to find where it's increasing and decreasing and to find our critical points. So we have critical points at 0 and 2. So we can use our first derivative test, and we can check those intervals. So we know that our curve goes up and then down and then up. So we know we have a maximum value when x equals 1, a minimum when x equals 2. And just a note, we use this chart to help organize our thoughts, but on the AP test, when you're asked to justify why you have a max or a min, simply writing the chart, showing the chart isn't enough information. You have to put that into words. And it would look something like this. So there's a local maximum at 0, 4 because y prime is greater than 0 for all x from negative infinity to 0, and y prime is less than 0 for all x from 0 to 2, implying that the curve goes up and then it goes down. And we could use a similar explanation for our local minimum at 2, 0. So we're just putting the information in the chart into words to show that we truly understand what those symbols mean. We also could have used the second derivative test. If we take the second derivative, when x is 0, that's negative, so it's concave down, we have a maximum. If we take the second derivative at 2, we get positive 6, that's concave up, so there's a minimum. So just to be clear, we proved where we have a max and a min using two different methods. In practice, you would just have to choose one or the other. Okay, so if we're looking for inflection points, y double prime is 6x minus 6. We set that equal to 0. So x equals 1. And we can use a number line with the second derivative. Check numbers to the left and right of 1 using the equation for the second derivative, 6x minus 6. And we can find that this curve is concave down from negative infinity to 1 and concave up from 1 to infinity. And now we can put all this information together. So we have roots at negative 1 and 2, so we can plot those points. We're increasing from negative infinity to 0 and 2 to infinity, decreasing from 0 to 2. We have our maximum value, we have our minimum value. We know that we're concave down from negative infinity to 1, concave up from 1 to infinity, and we have an inflection point at 1, 2. So putting that all together, our curve looks something like this.